The central problems in machine learning are model selection and model assessment. Model selection is the process of choosing the best model to be deployed from among a collection of candidate machine learning models trained on the observed data. Once a model is chosen, before its deployment, we need to evaluate it in order to know how well it is expected to perform in general. This is the model assessment. Model selection can be applied both across different types of representation, such as linear models, neural network, decision trees, or across models of the same type configured with different models' hyperparameter, such as the regularization parameter in ridge regression or the number of layers and neurons in neural network, or across different input spaces, obtained through feature selection or dimensionality reduction techniques. Once we have generated different candidate models, how can we choose the best one? The choice of a machine learning model is influenced by many constraints related to the available computational resources, requirements from project stakeholders, interpretability of the model, and many others. Here, best means the model with the minimum predictive error with respect to the true function. Unfortunately, since the true function is unknown, we don't have access to the predictive error, but we can try to estimate it from the data. To estimate the predictive error, we cannot use the training error, as it is optimistically biased. A model selection based on the training error will always choose the most complex model. In fact, models with high complexity will have lower training errors compared to simpler ones, thus leading to overfitting. In order to have an unbiased estimate of the prediction error, we cannot use all the available data for training. We need to keep some of them for model selection and others for model assessment. One solution is to split the data into training, validation, and test sets. We fit candidate models on the training set, evaluate and select them on the validation set, and report the performance of the final model on the test set. To have a robust process, we would need many samples in each one of these three datasets. In many applications, however, the data availability is limited, and we wish to make the best use possible of the data. When data is limited, we can resort to one of these two classes of model selection techniques: probabilistic measure and resampling methods. Probabilistic measures involve analytically scoring a candidate model using both its performance on the training dataset and the complexity of the model. The idea is to penalize the training error, which is optimistically biased, based on the complexity of the model. A model with fewer parameters is less complex, and because of this, is preferred because it is likely to generalize better on average. Some commonly used probabilistic measures are the Akaika information criterion, the Bayesian information criterion, the minimum description length, and the structural risk minimization. Probabilistic measures are appropriate when using simple linear models, like linear regression or logistic regression, where the calculation of model complexity penalty is known and tractable. On the other hand, resampling methods seek to estimate the performance of a model on out-of-sample data. This is achieved by splitting the training dataset into subtrain and test sets, fitting a model on the subtrain set and evaluating it on the test set. This process may then be repeated multiple times, and the mean performance across each trial is reported. It is a type of Monte Carlo estimate of model performance on out-of-sample data. Although each trial is not strictly independent, as depending on the resampling method chosen, the same data may appear multiple times in different training datasets or test datasets. By far, the most popular is the cross-validation family of methods that includes many subtypes. An example is the widely used k-fold cross-validation that splits the training dataset into k-folds. The general procedure is as follows. First, shuffle the dataset randomly. Second, split this dataset into k groups. Third, for each of them, we have two. Take the group as a holdout or test dataset. Take the remaining group as a training dataset. Fit the model on the training set and evaluate it on the test set. Retrain the evaluation score and discard the model. The fourth and last step of the general procedure is to summarize the skill of the model using the sample of model evaluation scores. Importantly, each observation in the data sample is assigned to an individual group and stays in that group for the duration of the procedure. This means that each sample is given the opportunity to be used in the holdout set one time and used to train the model k-1 times. The larger is the number of faults k, the better is the estimation of the error. But it comes at the price of a higher computational cost, as k models need to be trained. Once the model selection process has been completed, how can we assess the performance of the selected model? We can use neither its training error nor its validation error, as both are optimistically biased. To get an unbiased estimate of the performance of the selected model, we need to resort to the test set, which contains data that was not involved in the learning process. Pay attention! If the performance of the model is not satisfactory, we cannot reuse the same test set to evaluate the performance of new models, as it will be no longer unbiased, and the risk is to overfit it. In this case, we will need to have a different test set with fresh new data. Proper model selection and model assessment procedures are fundamental to successfully solving supervised learning problems. Starting from the next lesson, we will move to unsupervised learning, the subfield of machine learning that tries to find the inner structure in the data in order to build better representations.